Hello everyone. Welcome to the 10th lecture on partial differentiation. In this lecture, we'll discuss about maxima minima of functions of two variables. Here we have a function z, which is a function of two variables x and y. We know that a function of two variables is represented in a three-dimensional space. Here we have x-axis, y-axis and z-axis, and this surface represents the function fxy. Now to find out what is the maximum value of this function, that means we have to find out a point where the function has a maximum value. Now the function f of xy is said to have a maximum value at the point AB if there exists a neighborhood of AB such that f of AB is always greater than the value of the function at the neighborhood points of AB. Here, in this surface, we can see it clearly that this point is the point where the function has the maximum value. So we can say that at this point AB, the function has a maximum value. Clearly, we can see here that the value of the function at this point AB is always greater than the value of the function at neighboring points. If we take a neighboring point a plus h, b plus k around this AB, value of the function at a plus h, b plus k is less than the value of at AB. That means if our a plus h, b plus k is here and value of the function at this point is lying here on the surface. And it is very clear from this figure that value of the function at AB is here and value of the function at a neighboring point a plus h, b plus k is here. If our point is here, a plus h, b plus k is here, then value is here. So the definition, the function fxy is said to have a maximum value at AB if there exists a neighborhood of AB such that fab is greater than f of a plus h, b plus k. Now what is the minimum value of the function? The function fxy is said to have a minimum value at AB if there exists a neighborhood of AB such that fab is less than f of a plus h, b plus k. Let us consider this figure. Here we have xyz plane and here we have the function fxy. Now it is clear that this is the minimum point. Here we have a point on xy plane at which the value of the function is minimum, this point. So here we have AB and the value of the function at this point AB is always less than the value of the function at its neighboring points. If we take a neighborhood point here a plus h, b plus k, then the value of the function at this point a plus h, b plus k is here on the surface. And this is greater than the value of the function at at AB. So here we have seen that the point AB is the point where the function has minimum value because f of AB is always less than f a plus h, b plus k. The function f of xy is said to have a saddle point at the point AB if the point is neither a point of maximum nor a point of minimum. Let us consider this figure. In this figure, this point is the saddle point because this point is neither a point of maximum nor a point of minimum. At such point, the function f of xy is maximum in one direction and minimum in other direction. We can see here that this point in this direction, it is the point of minimum, and in this direction, this point is point of maximum. So the function f of xy is said to have a saddle point at AB if the point is neither a point of maximum nor a point of minimum. The maximum and minimum values of a function are also called extreme values of the function. Now let us find out some necessary and sufficient condition for extreme values. Let z is equal to f of xy be a function of two variables x and y. Then the function f of xy is said to have maximum value at the point AB if f of AB is greater than f of a plus h b plus k. And the function is said to have a minimum value at this point AB if f of AB is less than f of a plus h b plus k. In other words, we can say that if f a plus h b plus k minus f of a b is less than 0, that means negative, then the function has a maximum value at the point a b. And if the difference f a plus h b plus k minus f of a b is positive or greater than 0, then the function has a minimum value at the point a b. Thus, the extreme values of the function depends on the sign of this difference. F a plus h b plus k minus f a b. Let us denote this difference with a symbol delta f. The extreme values of the function depends upon the sign of this difference f a plus h b plus k minus f a b. Let us denote this difference as delta f. Now we have to check about the sign of this difference. By Taylor's theorem, we have the expansion for f a plus h b plus k. And we have seen in the Taylor's theorem that f a plus h b plus k is equal to f of a b plus h del by del x plus k del by del y f of a b plus 1 by factorial to h square del square divided by del x square plus 2hk del square divided by del x del y plus k square del square divided by del y square f a b, like this. Now this difference del f can be written in this way. F a plus h b plus k minus f a b is equal to this. Now we have to check about the sign of this difference del f. Sign of del f will depend on the sign of the leading term. In this case, the leading term is this h del by del x plus k del by del y f of xy. Because for higher order terms, because the value of h and k are very small, the higher order terms will be much more smaller than the leading term. So the sign of this difference depends upon the leading term only. So if we consider the first term of this difference, our first term of the difference is h del by del x plus k del by del y. This del by del x is the partial derivative of the function at x with respect to x at ab, and del by del y f ab is partial derivative of the function f with respect to y at ab. Now let us consider this first term for different values of h and k. If our h is 0, then the first term we have, in the first term we have k del by del y of f ab. If h is equal to 0, in the first term we have this k del f by del y of ab, partial derivative of the function with respect to y at the point ab. Now del f by del y is either positive or negative at ab, because the partial derivative of the function f with respect to y at ab is either positive or negative. If this partial derivative of the function with respect to y at the point AB is positive, then k del f by del y is positive for k positive. If our k is positive, then this product k into del f by del y is positive because del f by del y is positive. But if k is negative, then this product will be negative. If the partial derivative of the function with respect to y is negative, then we can here see that the product k del f by del y is positive if k is negative, and the product is negative if k is positive. So in this case, we have seen that this for k is positive, for k is positive, the sign of the product is, in one case it is positive and in the other case it is negative. So the sign of k del f by del y doesn't remain same for all points in the neighborhood of AB. If we fix a point k, and we have seen that for k is positive, the sign of this product k del f by del y is in one case positive and in other case it is negative. So this sign of this product doesn't remain same for all points in the neighborhood of AB. That means it doesn't remain either positive or negative around all the points of the neighborhood of AB. Similarly, if we consider k is equal to 0 in the first term, we have this, because in our first term we have h del by del x plus k del by del y of FAB. If our k is 0, then this term will become 0. Now we have with us only h del by del x of FAB. So we have here with us h del f by del x at AB. Now in this case also we can see that this partial derivative of the function with respect to x is either positive or negative. If it is positive at AB, then the product h del f by del x is positive if h is positive, and it is negative if h is negative. Similarly, if this partial derivative is negative at this point, then the product is negative for h is positive and it is positive for h is negative. Here also we have seen that the sign of h del f by del x doesn't remain same for all points in the neighborhood of AB. So the first term of the difference del f doesn't decide about the sign of the difference, because for a neighborhood point, this h del by del x plus k del by del y is changing its sign. So the sign of the difference del f will depend upon the next leading term. As we have seen, sign of h del by del x plus k del by del y at AB will remain same, either positive or negative, in all points of the neighborhood of AB if both the partial derivatives del f by del x and del f by del y are 0 at the point AB. Because at this point we have seen that this term is changing its sign around the neighborhood points for any values of k or h. So the point AB is a point of maximum or a point of minimum only if both del f by del x and del f by del y are 0. Thus the necessary condition for the extreme value of the function fxy is, if function possesses an extreme value, either maximum or minimum at the point AB, then the partial derivative of the function with respect to x is 0 and partial derivative of the function f with respect to y at AB is 0. So this is the necessary condition. As we have discussed that the sign of delta f, the difference fa plus h b plus k minus fab, doesn't depend upon the sign of the first leading term, but it depends upon the next leading term, because first leading term is changing its sign around the neighborhood points of AB. So now let us check about the sign of the second leading term of the difference. Now the second leading term of the difference delta f is 1 by factorial 2 h square del square divided by del x square plus 2 hk del square divided by del x del y plus k square del square divided by del y square FAB. Now let us use some notations to simplify this expression. Let us use some notation for higher order partial derivatives. Now let us denote R as the second order partial derivative of the function f with respect to x at AB. That means del square f divided by del x square at AB is denoted as R. Similarly, del square f divided by del x del y at AB is denoted as S, and del square f divided by del y square at AB is denoted as T. So the second leading term is converted to 1 by 2 h square r plus 2 hks plus k square t. Now the sign of this difference delta f will depend upon the sign of this second leading term. Now let us proceed further. This term h square r plus 2hks plus k square t, we have multiplied r here and divided r. So the sign of delta f is equal to sign of 1 by 2 into 1 by r h square r square plus 2hkrs plus k square rt, which is equal to sine of 1 upon r h square r square plus 2k h rs plus k square s square plus k square rt minus k square s square. Here we have just added one term k square s square and subtracted the same term from this. And as in the second line we have here 1 by 2, we have dropped this 1 by 2 because by dropping 1 by 2 the sign of the function will remain same, which is equal to sine of 1 upon r this h square r square plus 2hkrs plus ks, k square s square is nothing but hr plus ks whole square. Similarly, from this k square rt minus k square s square, we have taken common k square. Now we have only rt minus h square, which is equal to sine of 1 upon r k square rt minus s square, because the sign of h r plus ks whole square is always positive. So by dropping this positive term from this expression, sign of this expression doesn't change. So finally we have sine of delta f is equal to sine of 1 upon r k square into rt minus h square. So here we have with us sine of the delta f is equal to sine of 1 divided by r k square into rt minus h square. Now here three cases are there. If rt minus h square is greater than 0, or it is less than 0, or it is equal to 0. Now let us study one by one. The first case is if rt minus h square is positive, it is greater than 0. Then sine of delta f is greater than 0 if r is greater than 0. Because if rt minus h square is greater than 0 and r is greater than 0, then the sign of entire the term is positive. Similarly, if r is negative, then sign of this entire term is negative because rt minus h square is positive. So if r is positive, delta f is positive. If r is negative, then delta f is negative. Therefore, if rt minus h square is greater than 0, then the function f of xy has a maximum value at the point ab if r is less than 0. And the function f of xy has a minimum value at the point AB if r is greater than 0. So this is first case. Now in case 2, if rt minus a square is less than 0, if it is negative. Now let us consider the difference delta f. We have sine of delta f is equal to sine of 1 upon r h r plus k s whole square plus k square into rt minus h square. Now if this rt minus s square is negative and for k is equal to 0, if our k is 0, then what happens? Then the second term here k square into rt minus s square will become 0. Now we have only 1 upon r hr plus ks whole square with us. So the sign of this difference delta f is positive if r is positive, because here k is 0, so we have with us only this. If r is positive and this h r plus k s whole square is always positive, So delta f, sign of delta f is positive. If r is negative, then sign of delta f is negative. But if k is not equal to 0, if this k is not equal to 0, what happens? If k is not equal to 0, then this second term is negative, because here we have k square, it is a positive term, and rt minus s square is negative, because this second case is for rt minus s square is negative. So this second term is negative. And here we have hr plus ks whole square. Here we can find out certain values of h and k for which this expression becomes 0. That means hr plus ks will become 0. For that we have to find out one h which is equal to minus ks divided by r. If we can select h as minus ks divided by r, then this expression will become 0. So what we have only with us here? Sine of 1 upon r, sine of 1 upon r into this is 0. So only k square rt minus h square, and this term is negative. This term is negative. So sine of delta f will depend upon the value of r. If r is positive, it is negative, because this second term is negative. K square into rt minus s square is negative. So the sine of delta f is negative for r is positive, and sine of delta f is positive for r is negative. So here what we have seen that in this case we observed that for r is greater than 0, here in the case of r is greater than 0, in one case delta f is negative, and in the other case delta f is positive. Sign of delta f is positive if k is equal to 0, and it is negative if k is not equal to 0 in the case of r is greater than 0. So delta f is changing its sign in the neighborhood of ab if rt minus s square is less than 0. Since delta f is changing its sign in the neighborhood of AB, if RT minus S square is negative, therefore if it is negative, then the point AB is neither a point of maxima nor a point of minima. Rather, in this case, if RT minus S square is negative, we can say that this point AB is a saddle point. Hence, if RT minus S square is negative, then AB is a saddle point. Now let us discuss about case 3. If RT minus S square is equal to 0, then this expression, the difference 1 divided by R into H R plus Ks whole square plus K square into RT minus S square becomes 1 upon R H R plus Ks whole square. Because if this is 0, this second term becomes 0. So we have only this with us, 1 divided by R into HR plus Ks whole square. But we can choose the values of hk in such a way that this becomes 0. Hr plus ks is equal to 0. As we have seen in the previous slide also, we can choose h in this way. H is equal to minus ks divided by r. Then this expression becomes 0. Thus, in this case, the entire term 1 divided by r, hr plus ks whole square plus k square into rt minus h square becomes 0 for some values of h and k. If we choose h and k in this way, for any value of k we can find out h, and for this value this first term will become 0, and in this case 3 we have already assumed that rt minus h square is 0, so the second term is 0, so the entire term becomes 0. Therefore, if RT minus S square is 0, then further investigation is required to find out maxima and minima. This test, in this test, we cannot find out whether the point AB is a point of maxima or a point of minima if RT minus S square is equal to 0. Therefore, further investigation is required. Now let us summarize what we have studied in this lecture. The working rule for maxima minima. Let z is equal to fxy be a function of two variables x and y. Then the first step is to evaluate the partial derivative of the function f with respect to x and partial derivative of the function f with respect to y. Then in the second step, we have to equate the partial derivative del f divided by del x to 0 and the partial derivative del f by del y to 0. We have to equate these two partial derivatives to 0 to obtain the point AB. This is the necessary condition what we have studied in the slide in this lecture, that if A, B are extremum points, then the partial derivative of the function with respect to x and y at this point is 0. The next step, you evaluate the higher order derivatives R A S T at AB, where your R is del square f divided by del x square, S is del square f divided by del x del y, T is del square f divided by del y square. The next step is if RT minus h square is positive, then the function f of xy has a maximum value at AB if R is negative, and the function has a minimum value at the point AB if R is positive. If RT minus h square is negative, then the function f of xy has a saddle point at the point AB. And if RT minus h square is 0, then further investigation is required to obtain maxima and minima. This is all about the maxima minima for functions of two variables. In the next lecture, we'll discuss on some examples and problems based upon maxima minima.